Hello my friends, welcome. I'm really glad you're here. Wherever you're watching from, whatever brought you to this video, thank you for giving me your time. I want you to imagine that we're sitting together, calmly, curiously, ready to look at the world a little differently than we did before. What if I told you that something Isaac Newton explained in school was misunderstood, not wrong, but incomplete in the way it was taught? What if I told you that physics works differently than most people remember learning it? And what if the ordinary world around you, your walk, your breath, the quiet motion of the air, was already showing you the truth every second of your life? That's what this documentary is about. Not myths. Not conspiracies. Just real, proven physics, rooted in Newton's ideas, refined by centuries of science, and explained in a way that actually makes sense when you look at everyday reality. Before we go any further, I want to ask you directly, if this video sparks even one new way of seeing the world, please like it. And if a thought or question comes to you while watching, share it in the comments. Physics is not something we passively consume, it's something we understand better when we interact, reflect, and discuss. Your engagement genuinely helps learning go deeper, for you and for others. When I was a student, physics felt like a collection of frozen diagrams. Arrows on a board. Balls rolling on frictionless planes that didn't exist. Equations copied neatly, memorized, tested, and then forgotten. Motion was something that started and stopped. A push caused movement. No push meant rest. Simple. Clean. Finished, but that picture is misleading because in reality, stillness is almost always an illusion. Right now, as you're watching this, you may feel completely still. Your chair isn't moving. The room seems calm. Nothing dramatic is happening. And yet, from a physics point of view, you are in extraordinary motion. You are rotating with the Earth at hundreds of meters per second. You are orbiting the Sun at roughly 30 kilometers per second. The Sun itself is moving through the galaxy, carrying us along, and even within your body, atoms vibrate, electrons move, energy flows. Nothing has stopped. This is not poetic exaggeration. This is measurable, established physics. And this is where Newton truly begins, not with objects at rest, but with motion that does not need permission to exist. Newton's first law is often taught like this: an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. Most people hear that and think, motion requires force to continue. But Newton was saying the opposite. Motion does not need force. Change needs force. Stopping needs force. Turning needs force. Motion itself is natural. This idea is called inertia, and it is one of the most misunderstood concepts in physics education. We are taught it in a world full of friction, air resistance, and constant interference, so it never feels true. But strip those things away, even mentally, and Newton's insight becomes clear. If nothing interferes, motion never stops. Think about that carefully. Not slows down. Not eventually rests. Never stops. In space, far from stars, far from particles, an object moving at a constant speed in a straight line will do so forever. There is no cosmic rule demanding that it come to rest. Rest is not the default state. Motion is, and this is where many people misunderstand Newton. They imagine he was describing an idealized exception. In fact, he was describing the fundamental rule, and friction is the exception. Everyday experience teaches us the wrong lesson because we live inside a thick soup of forces. Air pushes back. Surfaces scrape. Energy leaks away as heat and sound. So when you roll a ball, it slows down. When you stop pushing a box, it stops moving. It feels intuitive to think motion requires effort, but Newton asked a different question: what would happen if nothing interfered? And the answer changed physics forever. Motion continues. This idea forces us to rethink what force actually does. Force is not what keeps things moving. Force is what changes motion. It bends paths. It speeds things up. It slows them down. It rotates them. But without force, motion is perfectly content to continue exactly as it is. This is not abstract philosophy. You experience it every time you're in a car that suddenly stops. Your body keeps moving forward, not because something is pushing you, but because nothing has yet stopped you. Your seatbelt doesn't cause motion. It changes it. Newton didn't invent this behavior. He described it clearly for the first time, in a language precise enough to be tested. And this brings us to something important: Newton's laws were never meant to live on a chalkboard. They describe reality as it behaves everywhere, all the time, whether we notice or not. When a planet orbits a star, it isn't being pulled forward along its path. It is moving forward naturally, continuously, endlessly. Gravity doesn't make it move, it makes it turn. This distinction is crucial. Without gravity, Earth would not stop. It would fly off in a straight line, continuing its motion through space. Gravity doesn't create motion. It curves motion that already exists. That's not a correction of Newton, it's a fulfillment of his insight. As centuries passed, scientists refined this understanding. Einstein would later show that gravity isn't even a force in the traditional sense, but a curvature of spacetime. Yet even there, the heart of the idea remains: objects follow motion naturally unless something changes the rules. So why does this matter to you, here, now? Because it means the universe is not a machine that needs constant pushing. It is a system already in motion, already unfolding, already moving with extraordinary consistency. We don't live in a static world occasionally disturbed by forces. We live in a moving world occasionally redirected by them. When you drop a cup, gravity doesn't start the fall. The cup was already moving with Earth through space. Gravity changes the direction of that motion, guiding it toward the ground. When you jump, you don't escape motion, you redirect it upward briefly, then gravity curves it back down. Even when you sit still, motion is not absent. It is balanced. This is another idea that school often blurs. Rest is not the absence of motion, it is the balance of motion. Forces cancel. Velocities align. But movement at deeper levels continues relentlessly. Atoms vibrate even at temperatures near absolute zero. Fields fluctuate. Energy transfers. The universe refuses to be still. Newton understood this intuitively, even without modern instruments. His genius wasn't just mathematics, it was restraint. He didn't invent unnecessary mechanisms. He described what motion does when left alone, and what it does is continued. This realization changes how we think about cause and effect. It tells us that the universe does not need constant instruction. It follows rules that are simple, consistent, and astonishingly patient. Motion is not fragile. It does not fade unless something makes it fade, and this sets the stage for everything that follows: acceleration, force, momentum, energy, and even time itself. Because once you understand that motion never stops, you begin to ask a deeper question. If motion is natural, what does it mean to change it? That question leads us directly into the heart of physics. Most of us grow up with an intuitive picture. You push something, it moves. You stop pushing, it stops. Force causes motion. End of story. But Newton saw something different. Force does not create motion, force changes motion. This distinction may sound small, but it is one of the deepest ideas in all of physics. Let's slow down and really look at this. Imagine a puck gliding on perfectly smooth ice. Not real ice, perfect ice. No friction. No air resistance. You give it a push, and it slides away. Now here's the key moment: once you stop pushing, the puck does not slow down. It does not get tired. It does not use up its motion. It keeps going. The push did not give the puck motion. The push changed its motion from rest to movement. After that, motion belonged to the puck itself. Newton formalized this insight with his second law, which is often reduced to a famous equation: F equals ma, force equals mass times acceleration. But what matters is not the equation, it's the meaning. Notice what's missing from that formula. There is no velocity term. No position term. Force is not linked to how fast something is moving, or where it is. Force is linked only to acceleration. To change acceleration doesn't just mean speeding up. It means any change in velocity. Speeding up, slowing down, or changing direction all count as acceleration. This is where everyday intuition fails us again. When a car moves at a constant speed in a straight line, no net force is required. The engine isn't creating motion, it's only compensating for friction and air resistance. Remove those, and the engine could turn off forever. When a satellite orbits Earth, it is constantly accelerating, not because its speed is changing, but because its direction is. Gravity is not pulling it forward, it is bending its path. Acceleration is the true signal of force. This is one of the reasons physics feels strange at first. Our senses are tuned to velocity, not acceleration. We feel sudden changes, jerks, turns, stops, but we don't feel constant motion. If an airplane cruises smoothly, you feel still. If it accelerates, you feel pressed into your seat. Your body is an accelerometer, not a speedometer. Newton realized this centuries before the term existed, and this realization opens a door to understanding nearly everything that happens around you. Take something simple: throwing a ball straight up. It leaves your hand moving upward. At that moment, gravity is already acting on it, but gravity doesn't immediately stop the motion. Instead, it continuously changes it. The ball slows, moment by moment, until its upward velocity reaches zero. Then gravity continues changing the motion, and the ball accelerates downward. At no point does gravity turn on or off. At no point does motion vanish. Only direction and speed change. This continuous, patient reshaping of motion is how the universe operates. Newton's second law tells us something else that often goes unnoticed: mass is resistance to change. The more massive something is, the harder it is to accelerate. Not to move, to change its motion. This is why pushing a bicycle feels different from pushing a car. Both can move. Both can roll. But changing the car's motion, speeding it up, slowing it down, turning it, requires far more force. Mass is not just how much stuff there is. It is inertia quantified. It is the stubbornness of motion, and this leads to a profound insight: motion has persistence. It resists interference. The universe does not casually redirect things. Every change has a cost. This is why physics feels conservative. Energy doesn't appear from nowhere. Momentum doesn't vanish without trace. Every push is answered by resistance. Every action leaves a footprint. Newton captured this beautifully in his third law: for every action, there is an equal and opposite reaction. This is not a moral statement. It's a structural one. When you push on the ground pushes back. That's why you can walk. When a rocket fires, it doesn't push against space, it pushes against its own exhaust. The reaction is what accelerates it forward. Nothing moves alone. Every change in motion is shared between interacting systems. Forces come in pairs, always. This is another place where everyday language misleads us. We say the earth pulls the apple down, but the apple pulls the earth up with equal force. The difference is mass. The earth's acceleration is tiny, the apple's is obvious, but the interaction is mutual. Newton did not imagine forces as one-sided commands. He saw them as relationships, and this relational view is critical for understanding motion in the real world. It tells us that nothing happens in isolation. Every acceleration connects objects together, even if the connection is invisible. This is why physics feels so deeply interconnected. Because it is now, let's return to the idea that motion never stops. If force only changes motion, and motion is naturally persistent, then the universe is not driven, it is guided. This is why orbits are stable. This is why waves propagate. This is why momentum carries through collisions. This is why the past matters as motion carries memory. When two objects collide, the outcome depends on how they were moving before contact. Physics does not reset at each interaction. It evolves continuously, and this evolution is lawful. Newton's laws are not arbitrary rules imposed on nature. They are descriptions of how change unfolds when motion is allowed to be itself. Modern physics has refined these ideas. We now speak of fields, space-time, quantum probabilities. But Newton's framework still works astonishingly well for the everyday world, and for much of the universe beyond it. He didn't give us the final word. He gave us the grammar, and once you understand that grammar, you begin to read reality differently. A falling leaf is not obeying gravity, it is following a curved path shaped by forces acting on its existing motion. A spinning planet is not held in place, it is constantly being redirected. Even light, which Newton could only partially understand, follows paths defined by change rather than rest. Nothing is ever simply moving or not moving, everything is always becoming, and this brings us to an even deeper realization, one that often surprises people when they first encounter it. There is no absolute rest frame in the universe, motion is always relative. Newton himself believed in absolute space, but his laws quietly point beyond it. Later scientists would make this explicit, showing that motion can only be measured relative to something else. There is no universal stillness to compare against. This doesn't weaken physics. It strengthens it. It means the laws apply everywhere, for everyone, in every reference frame, and it means that when we talk about motion never stopping, we're not talking about speed, we're talking about continuity. The universe does not pause. It does not reset. It flows. Understanding force as change, not cause, allows us to see this flow clearly, and once you see it, you start noticing it everywhere, in the way crowds move, in the way rivers curve, in the way habits persist, in the way systems resist sudden shifts. Physics becomes less about equations and more about intuition grounded in reality. In the next chapter, we'll take this understanding and apply it to something even more fundamental: momentum and energy, why motion is conserved, how change is distributed, and why the universe has a deep preference for balance over chaos. If motion never stops, and force only changes it, then the next question is unavoidable: what, exactly, is being carried forward through time? The answer is not just speed. It's not just position. It's something deeper, something conserved. This is where physics reveals one of its most powerful ideas: momentum. Momentum is the memory of motion. Newton defined momentum simply as mass times velocity. Again, the equation matters less than the insight. Momentum combines how much something is moving with how hard it is to change. A slow-moving truck can have more momentum than a fast-moving bicycle. Mass matters, but the most important thing about momentum is this: in a closed system, it is conserved. That means it does not disappear. It does not get destroyed. It gets transferred. This is not a philosophical preference. It is an experimental fact confirmed in every collision, explosion, and interaction we've ever measured. When two objects collide, their individual motions may change dramatically, but the total momentum before and after remains the same, provided no external forces act. This is why physics feels fair. Not emotionally fair, but structurally fair. The universe keeps its books balanced. If one object gains momentum, another must lose it. If motion changes direction here, it changes somewhere else in response. Nothing gets a free pass. Think about a simple example: billiard balls on a table. One ball strikes another and stops. The second ball rolls away with nearly the same speed. Motion didn't vanish. It moved. This is not because billiard balls are special. It's because the universe enforces continuity. Momentum explains why recoil exists, why explosions spread symmetrically, why you lean backward when throwing something heavy, and once you see momentum as memory, collisions stop feeling violent and start feeling logical. The past shapes the future in a precise, measurable way, but momentum is only part of the story. There is another conserved quantity that often feels more mysterious: energy. Energy is harder to define intuitively, and that's why it's often misunderstood. People talk about it as if it were a substance, something stored, used up, or created. In physics, energy is not a thing. It is a bookkeeping principle. Energy measures the ability of a system to cause change. Unlike momentum, energy is conserved. It changes form, it moves between systems, but the total remains constant. Kinetic energy becomes heat. Potential energy becomes motion. Chemical energy becomes light and sound. But the accounting always works. This conservation is not an assumption, it's an observation that has never failed. Newton didn't use the modern language of energy, but his laws imply it. Later physicists formalized it, and it became one of the deepest guiding principles in science. What matters for our story is this: motion is never lost, only redistributed. When friction slows an object, the motion doesn't disappear. It becomes microscopic motion, heat, vibration, sound. The world warms by an immeasurable amount, but the energy is still there. The universe never forgets. This idea has enormous consequences. It means time has direction. It means systems evolve predictably. It means cause and effect are linked by conservation, not coincidence, and it means that when we say motion never stops, we are not just talking about visible movement. We are talking about motion at every scale, continuously transformed. Now let's connect this back to Newton and everyday reality. When you walk, your body's chemical energy becomes kinetic energy. Your foot pushes backward on the ground. The ground pushes you forward. Momentum flows through you into the earth and back again. Walking is not magic. It's controlled momentum exchange. When you jump, you don't escape gravity, you store energy in compressed muscles, release it as motion, then let gravity reshape that motion. Even standing still requires constant energy, because your body is balancing forces and correcting motion at every moment. Stillness is active. This is something Newton could not fully see, but his framework made it inevitable. Motion at small scales underlies what we perceive as rest. Modern physics has shown us that even in solids, atoms vibrate. Even in cold environments, quantum motion persists. Zero motion is not physically achievable. The universe enforces activity. Now, here's where things get truly interesting. Momentum and energy don't just persist, they interact. When objects collide, momentum determines the direction and speed after the collision. Energy determines how elastic the interaction is, whether objects bounce, stick, or deform together. These principles allow us to predict the future. Physics is not about control. It's about foresight. If you know the momentum and energy of a system, you can calculate how it will evolve. This is why Newton's mechanics were revolutionary. They turned nature into something readable. For the first time, motion was not mysterious. It was lawful, but this lawfulness doesn't mean rigidity. It means consistency. The universe does not improvise. It responds. This is why large systems, like weather, oceans, and galaxies, can be complex without being random. Their behavior emerges from countless momentum exchanges and energy transfers, all following simple rules. Chaos, in physics, is not disorder. It's sensitivity. Small changes in initial motion can lead to large differences later. But the underlying laws remain unchanged. Momentum still balances. Energy still conserves. This is another reason Newton matters today. His ideas scale. They work for apples and planets, for projectiles and pendulums, for machines and mountains. Even when we move beyond Newton, into relativity and quantum mechanics, the conservation principles survive. They become more subtle, but they do not vanish. Motion's memory persists even when motion itself becomes probabilistic, and this brings us to something deeply human. We live inside this flow of conserved motion. Our actions ripple forward. Our energy choices matter. Our movements, however small, interact with the world in lawful ways. Physics does not strip the world of meaning. It reveals structure. When you understand momentum, you stop seeing motion as temporary. You see it as inherited. Every movement carries history, every interaction leaves a trace. This is why physics feels so strangely reassuring. The universe is not careless. It keeps track. In the next and final chapter, we'll step back and look at the bigger picture, how Newton's ideas lead us to modern physics, why motion without absolute rest changes how we think about reality, and what it truly means to say that motion never stops. If you take a step back now, after everything we've explored, something remarkable becomes clear. Physics is not primarily about objects. It is not even primarily about forces. Physics is about change, and motion is how change speaks. Newton gave us the first clear grammar for this language. He showed us that motion is not something the universe struggles to maintain. It is something the universe naturally does. What requires explanation is not why things move, but why they ever change how they move. This reversal of perspective is one of the quiet revolutions of science. Once you accept that motion never stops, the universe stops feeling mechanical and starts feeling continuous. Events are no longer isolated moments. They are transitions in an unbroken flow. This is where Newton's ideas, surprisingly, point beyond Newton himself. He believed in absolute space and absolute time, fixed stages on which motion occurred. But the behavior he described did not require those stages. Later, Einstein would recognize this and take the next step. Space and time are not backgrounds. They are participants. Motion does not happen in space-time. Motion shapes spacetime, yet even here, Newton's insight survives. Objects still follow paths unless something changes them. Acceleration still signals interaction. Conservation laws still govern what is possible. Modern physics did not discard Newton. It refined the meaning of his words, and this refinement leads us to a deeper understanding of rest. There is no universal stillness. There is no privileged frame of reference. Every observer measures motion relative to themselves. And the laws of physics do not care which observer you are. This is one of the most humbling discoveries in science. The universe does not favor your perspective. It treats all consistent viewpoints equally. This means that motion is not something you can escape by stopping. There is always another frame in which you are moving, but this is not a flaw, it is a feature. It tells us that motion is relational. It exists between things, not as an absolute property, and this brings us full circle to the idea that motion never stops, not because everything is rushing somewhere, but because relationships never freeze. Even when a system appears stable, it is dynamically balanced. Forces cancel. Energy flows invisibly. Motion continues beneath the surface. Think about a bridge. It stands still for decades. But internally, atoms vibrate. Loads shift. Temperatures change. The structure is constantly adjusting, constantly responding. Stillness is choreography. The same is true for stars, for ecosystems, for your own body. Your heartbeat is motion. Your thoughts are electrical motion. Your metabolism is chemical motion. Life itself is structured flow. Physics does not reduce life to machinery, it explains why machinery can exist at all. Now, let's return to the title of this documentary, Emotion Never Stops. This is not a slogan. It is a statement about continuity. Emotion never stops because stopping would require the universe to forget. It would require momentum to vanish, energy to disappear, relationships to dissolve. That does not happen. Instead, motion transforms, and this transformation gives us time. Time, in physics, is not a ticking clock imposed from outside. It is a measure of change. If nothing changed, time would be meaningless. But change is everywhere, so time flows. Newton treated time as absolute. Einstein showed that time is linked to motion. The faster you move, the differently you experience it. But again, the core idea remains, motion and time are inseparable. No motion, no time. This is why physics is not just about predicting trajectories, it is about understanding existence. When you watch something move, you are watching the universe express itself, and when you understand the rules of that expression, the world becomes less mysterious, not because it loses wonder, but because the wonder gains structure. Newton once said that he felt like a child playing on the seashore, while the great ocean of truth lay undiscovered before him. That humility is important. Physics does not claim final answers. It offers better questions. It invites you to look at everyday experiences, a falling object, a turning wheel, a quiet room, and see not simplicity, but depth. The ground beneath your feet is not static. It is in motion with the planet, the star, the galaxy, the silence around you is full of vibration, the rest you feel is balance, not absence. And once you see this, you never quite see the world the same way again. You begin to notice continuity where you once saw interruption. You notice flow where you once saw stillness. You notice lawfulness where you once saw coincidence. This is not about memorizing formulas. It is about perception. Physics, at its best, trains you to see reality as it is, dynamic, relational, and deeply consistent. So the next time someone tells you that motion requires effort, or that rest is the natural state of things, you'll know better. Motion is not the exception, motion is the rule. Everything else is just how it changes.